Okay, so now we have Jocelyn Chen from UT Austin, and she's going to talk about data extraction via semantic regular expression synthesis.
So, hi everyone, I'm Jocelyn. Thanks for coming to my talk. Today I'm going to tell you about data extraction via semantic regular expression synthesis. This is joint work with Arko, Banerjee, Çağatay, Demiralp, Durrett, and Işıl, Dillig. So first of all, let's start with talking about regex. So of course, as we all know, regex is everywhere, and it's very commonly applied in applications such as email validation, credit card matching, and also matching on HTML tags. However, there's one issue. As you can notice, all of these tasks focus on matching syntactic constraint. And the reason, let's look at why this might be potentially an issue by looking at a following task. So here I give you a data set where this data set describes a set of museum collection. And let's say user want to find all the European artists who were born before 20th century whose name contains Thomas. So if we think about how we achieve matching all the strings in this task, we can mainly divide into two types of way of, we can mainly categorize in two ways. So first of all, we need to think about how do we parse the comma separate string, because clearly this query is talking about the artist's bio column here. Also, we also want to think about how we match a string with the name Thomas. So I call these syntactic constraint. On the other side, we also have to think about which part of the string corresponds to name, how to find whether an artist is from Europe, and how do you check the birth year of an artist. And I call these semantic constraint. So if you think about using a regex to solve this task, I hope you can easily come to the conclusion that regex cannot easily solve this problem because there's a lack of support for semantic constraint. So in this work, I present Smore, which stands for semantic regular expression that support matching a combination of syntactic and semantic constraint. And this is rely on the idea of extending regular expression with semantic matching, where regular expression, of course, as we all know, is very good with syntactic matching, and we have some semantic matching mechanism to handle semantic constraint. So how exactly does it work? The core idea here is to interpret sequence of characters with some semantic meaning. So in terms of what that means, let's look through two examples. So first of all, if we want to match a string that's described 20K, in traditional regex, you might want to write a program which is concatenate 2 with 40. In semantic regex, this is just a number of value 20K. If you want to match like person name, like Taylor Swift, Lionel Messi, in traditional regex, you might want to write a program which is 2 words that start with a capital letter, concatenated by space. In semantic regex, that's just going to be celebrity person name. So here, I show you the syntax about how you would like to potentially write it in our language. Here, let's unwrap like why the syntax looks like this a little bit more. So I call this a semantic matcher, and hopefully you realize it looks really like a refinement type. And where here, the tau represent a base type. In fact, in your language, we support any type of type as long as it has some semantic meaning, like restaurant, product name, processor, you name it. One additional semantic matcher is a base type that's annotated with some logical qualifier. So here, instead of supporting any type, we only support a set of building types, like person, organization, integer. And the way that logical qualifier works is that given a string S, we first interpret as an object of a specific type, and then we check whether this object satisfies a certain predicate. So we support stuff like check number ranges, check date and time values, and also check like location properties. So if you're curious about how exactly this is implemented, we use a range of constructs from data-type parser, entity matchers, and of course, large language models. So here, I already talked about the syntax for semantic matchers. For the rest of the semantic regex language, we have all the regular constructs we normally see in regular expression, except the only thing is like the semantic matcher is a base case for the regex operator. So what exactly can this type of program can do? Suppose we want to match artist whose name contains Thomas. This is how we're going to write a semantic regex. So it's an intersection of a semantic constraint and syntactic constraint, where the first constraint is semantics. It has to describe a person name. And also, it has to, somewhere contain Thomas. if we want to match European artists who were born before 20th century in the context of our motivating example. So here we have a program that basically first talk about a country that's in Europe, concatenate with a comma, and a year that's less than 1900. So here I present you the language. However, there's one issue. Well, regex are hard to write. So as a second part of the talk, I'm going to talk about how we synthesize semantic regex from a few user label positive and negative examples. Well, first of all, since we're having very few user labeled positive examples, we have a couple challenges. For example, how do we generalize from a few, very few label examples, and how do we decide what semantic types to use? So one thing to emphasize here is that if you think from an enumerative synthesis perspective, since we support any type of base type, of course you cannot enumerate all possible base type in enumeration. So that's why this challenge comes from. Well, our key idea, again, is to use LLM to guide the synthesis procedure. So why using LLM, although everyone's using it, but let me try to convince you from analyzing the pros and cons of large language model. So on the pro side, large language model is very good at detecting text semantics. Well, because obviously this is what they are trained on. And it's also very good at generating regular expression because this has been all over the internet for years. On the other hand, it have a trouble doing precise reasoning that help us differentiate positive from negative examples. So by taking this idea, by relying on the pro side of our LLM, the first idea here, we're going to use LLM to generate what we call a typed regex sketch. So here I show you an example of typed regex sketch in the context of the motivating example. As you can see that this whole program looks pretty similar as like a regular expression, except the whole are annotated with some semantic type. So to handle the issue of how we differentiate positive from negative examples, we use program semantics to reason about how we differentiate. So let's take a detailed look at this synthesis workflow. We start with a set of positive and negative example provided by the user. We prompt the GPT and get some sketch, which we pass to the synthesizer. If we synthesize it successfully, we're all done. Otherwise, we go to the next sketch. First, let me elaborate how we do the sketch generation part. Well, we use prompting to generate the sketch. And specifically, we're asking it to summarize the structure of the positive examples. Because if user want to match something, there's probably some structure in the string that's shared in common. So here we give all the some sample example string as the positive example string. And here we give a label sketch. So in total, we provide 8 in-context example. And for each of the new tasks, we just append the query at the end of the prompt. And this is how we get the generated sketch. Once we have the sketch, we have to synthesize from the sketch. So since, as you can recall, every of our hosts is annotated with some semantic type, and apparently we can do type-directed synthesis here. However, there's 2 issues. So first of all, since a lot of time, the structure of the string might be really large, we might have a lot of hosts in our sketch. So one thing is very inefficient to synthesize all hosts at once. And second, since our sketch is generated by the LLM, which have no guarantee whether the sketch will actually lead to something that's meaningful, the sketch generating may be really incorrect. So in response to this challenge, we actually propose a following synthesis workflow that decomposes this whole thing. So given a sketch, we first run a decomposition procedure so that we, instead of generating synthesize on the whole sketch, we're dividing into subproblems. And if the synthesis is failing with respect to a single sketch, we try to use the feedback from the synthesizer to do sketch repair. So how do we do this? The highlight of our synthesis technique is to decompose, do the decomposition and repair using the concept of over-approximation. Over-approximation is commonly used across many literature, but let's just revisit what exactly that is. So a over-approximation, basically of a sketch, accept every string that can be accepted by any program that can synthesize from the sketch. So in the context of our motivating example, if we have the following sketch, one simple way to generate the over-approximation is just to replace all the hosts with dot star, because dot star can always match everything that can be matched by the whole. So how do we use it to generate the decomposition? Well, basically all we're doing here is just run this over approximation of the sketch over the positive examples. And we get the matched group string that matched by each of the single ho. And in this way, we actually obtain 4 subtasks where we can nicely decompose the positive example into 4 subtasks. And in this way, we can synthesize each ho pretty independently. So next, we're going to talk about how we use over approximation for sketch repair. So let's look at a different sketch, where here instead of like a year range, we have a year only. So this is a different sketch. By running the over approximation, we obtain these 3 subtasks. And if you can take a detailed look at this, you realize the last column for the positive example is hard to synthesize. But here it is year, but in fact here this is a year range. So the sketch generated is incorrect. The first step of doing sketch repair is through error localization. The way we're doing it is relying on the concept of over approximation again. By replacing each of the ho with over approximation, I keep running until we get a first error localization program that can accept all the positive examples. The more detail you can refer to or OOPSLA paper, but I'm just going to show you how we do the rest. So using this error localization program, we generate a repair specification where, as you can notice, it successfully locate the last ho to be the errored ho, and we also annotate with the set of positive examples. Again, we just prompt this single ho with the positive example to an LLM. We're able to obtain a new sketch, and you can see it's like a more refined version than the previous one we got. So that's all I'm going to talk about the technical part of the talk, and let's see how well it works. So specifically, we'll collect 50 tasks across 10 datasets in a various domains like sales, science, arts. For training, we propose 6 in total, positive and negative examples. And for testing, we have 20 separate test sets for each of the tasks for our synthesized program. So first part of evaluation is to compare our semantic regular expression against existing data automation baseline. And we compare against the following baseline, which the first is a traditional regular expression synthesizer. The second one is directly query, GPT 3.5, whether a string should be matched given the examples. And lastly, this is FlashGPT, which is extension of FlashWheel with GPT query ability. We evaluate in terms of F1 score and number of finished within 1 minute time limit. And you can see that in terms of both F1 score and number of finished, Smore does outperform existing work, except for the ChatGPT execution because there's no synthesis required. The next, let's look at how our tool or synthesis technique compared to existing baseline. And here we compare against a ChatGPT synthesizer with respect to our semantic regular DSL, and a Smore no sketch, which is a enumerated semantic regular synthesizer without sketch generation. And again, if you look at this graph, you can see that Smore outperforms existing work as well in terms of the way it can synthesize or not. So in this talk, I present you Smore, which is a language for supporting syntactic plus semantic string. And we also present you a synthesis workflow that can synthesize program for positive and negative examples. We do open source the code, so please try it out. And one more thing to add, I'm on the job market, so if you want to hire me or you're hiring, let me know. So yeah, that's it.
So thanks for the talk. So first I have like a clarification question because you mentioned you can have some sort of semantics. So in your template, like you have a regular expression that consists of 2 years. So can you say something like maybe the first year is earlier than the second year? So that is the kind of semantic constraint you can synthesize in this framework?
Yeah.
Okay, so then a follow-up question is, as far as I know, there are some existing language called OOPSLA, which can actually allows you to, you can say it's a first order logic over parse trees, which means you can have a context-free grammar. You can talking about, okay, what kind of relations we should have for these like non-terminal tokens, for example, non-terminal symbols and maybe some tokens, let's say. So do you think it's also possible to generate such, more expressive constraint because we know that regular is still very limited, let's say? And also that's why people make mistakes in validating email address, because email is not regular. I mean, yes, so do you think that this kind of like expressive constraint can also be synthesized using these large language models?
Yeah, I don't see a particular reason why it can't not, I guess. And it really depends on, I feel like similar kind of technique I'm presenting here can also be applied to this. I'm not sure about the over-approximation part because over-approximation is regular only. And you might have to think about other way to do over-approximation to decompose the task. But it's totally possible to support like, context-free language with semantic support and also synthesize from that. So I guess the answer is yes.
Okay, thanks.
Thanks for the talk. Super interesting stuff. One thing that struck me when, the question that I have is exactly what you didn't talk about, which is how exactly the matching algorithm works. Because when I think about regexes, I think about big 10,000 line files. Can you speak about efficiency, economics, matching?
Well, that's a good question. So I guess, well, first of all, to be really honest, we did not apply this technique to a very large file because of, the way it works is, first of all, you're going to do a pass over. So given you have the program, you already have a sense about what the semantics type are like, right? So basically, you kind of use various matchers. You pass your input string and the type to various matchers and generate all the possible set of substring. And this is where, you kind of get the context for the matching to start performing. If you use GPT all the time, of course, you're going to go bankrupt, probably. But, which probably drive the need for like, more specific type of tools like, entity matchers, you can run it for free at this point. And it works pretty well on like stuff like person name, organization name. So I think that kind of require more better optimization in terms of engineering, but I would not consider as like a fundamental bottleneck. Does that make sense? Yeah, cool.
Hi, so very short. So there's this model called symbolic automata, which has the similar structure. Have you looked into it? Because it seems like Smore is just regular expression with some alphabet theory, and you just have semantics, which is alphabet theory. So have you looked into symbolic automata, and do you know, like, is it similar, or is it something different?
I guess I'm not really sure what symbolic automata you're referring to. Is that kind of what you're kind of asking here?
It's basically an automata where you have alphabet theory. So you can say things like x greater than 2000 and whatever.
Oh, yeah. Okay. Yeah, sure. So I think, in this world I have not looked into, but I think there's a couple of ways you can frame this type of stuff in different type of theory other than like just regular expression. I'm happy to talk about it offline. I think I have a reviewer who talk about clean algebra with test. It's also something along this line, I guess. So I'm happy to talk more about it offline.
Okay, thank you.
Yeah.
Let's thank Jocelyn one more time.